And the last thing is Kepler's laws. Now, they are all in orange because it's very important that you know these definitions. Now, these are the 3 laws that Johannes Kepler formulated when he was studying the heavens. The law of orbits, which means that all planets move in elliptical orbits, with the sun at one focus. The law of areas, a line that connects the planet to the sun sweeps out equal areas in the plane of the planet's orbit in an equal time. That is, the rate of our change in area over change in time at which it sweeps out area A is constant. And the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit, and we'll see examples of all 3. Again, in this picture, we have the major axis labeled and the minor axis labeled, with the star at one focus. Again, all planets move in elliptical orbits unless the problem specifically says that it's moving in a circular orbit. Again, this picture kind of shows a really good example of the star at one focus. Also, Kepler's second law says that stars sweep out equal area in equal time. So this second picture shows that the area that it sweeps out here is same as the area swept out here, and the amount of time it took to sweep out that area is the same in both situations as well. Now, the most important part is this piece down here, that the star and planet both orbit around this center of mass. So if you're asked to draw the orbits, like in the first example problem given in the assignment, you need to solve for the center of mass, and that's going to be about the point where they orbit. And we'll see an example of that later. And the last one, Kepler's third law, the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis. What that means is if you start off with our gravitational force, and we know that this gravitational force is what keeps objects in orbit, meaning that it provides a centripetal force, then we can see that one of the masses will cancel out, and we're left with capital M, which is the mass of the planet. And again, one of these R's will cancel out. So remember that if it's moving in a circular orbit, that velocity was 2 pi r over t. Again, we're pulling a lot of stuff from mechanics back. So this piece becomes squared, and we get 4 pi squared r squared over t. And if we rearrange and solve for t squared, we get t squared equals 4 pi r squared, 4 pi squared. We're going to have r cubed over g times m. Now you can see that everything inside that I've circled is a constant, so my period only depends on the distance. Now again, this derivation is going to be important to be able to recreate. So one last thing about energy. Using our orbital speed derived from the Kepler's third law and the formula for kinetic energy, we can define the kinetic energy of an object in a bit more detail when it is in orbit around a body, which means it can be rewritten as 1/2 m times g times m over r. Again, if you look at this equation, this is just half of the potential energy equation. Now, the reason that this equation is so important is because this greatly simplifies the math. If we use regular kinetic energy along with potential, we will need both the orbital velocity and the orbital radius. In this case, we only need the orbital radius. So if we want to solve for the total energy, we wouldn't even have to use velocities. We can just use the equation that we just derived, which is this portion right here, plus our potential energy equation, which would give us negative g times m times capital M over 2r. And finally, as the radius of motion gets larger, the orbiting body's kinetic energy must decrease. Again, we know that if we throw an object up, its kinetic energy is going to slow down, but its potential energy will increase. So, as it slows down, its potential energy is going to increase, therefore become less negative. So saying become less negative means that we have to find our zero position for our potential energy at infinity.